Hi everyone, my name is Jiang, and today I'm going to be solving problem 5.18 in Griffith's Introduction to Electrodynamics. 5.18 states, show that the magnetic field of an infinite solenoid runs parallel to the axis, regardless of the cross-sectional shape of the coil, as long as the shape is constant along the length of the solenoid. What is the magnitude of the field inside and outside of such a coil? Show that the toroid field equation 5.60 reduces to the solenoid field when the radius of the donut is so large that a segment can be considered essentially straight. So the first part of this problem wants us to show that the field produced by an infinite solenoid runs parallel to the axis. And the axis they are referring to is a direction that the whole solenoid is extending in. So let's begin by visualizing such an solenoid. Here, I will begin by first drawing my axes. Here's X, Y, and Z. And suppose I'm going to consider two slices of this solenoid. One slice up here, and I'm going to draw them for any arbitrary shape. So this is at a height of Z prime. And then if I come down, I'll draw another loop or a slice of the same solenoid at negative Z prime. Okay. Now, since we are considering a solenoid, an infinite solenoid for that fact, that this will extend to negative infinity in the Z direction, and this one will also extend to positive infinity. Since we are saying that the shape of the solenoid stays constant, there is a point, or actually for every slice of the solenoid, we can say that there's another point on the solenoid, or rather, if you consider two slices of the solenoid, each slice will have a point that share the same X and Y component. So for instance, in this point, both of these points project onto the XY plane here. And they have a coordinate of X prime, Y prime, and then this is obviously 0. So let's pick a point on this XY plane to find the differential element of the magnetic field from each of these differential contributions on each of these points of the solenoid. Now, let's define up here, well, since both of these, let's say the current is going counterclockwise also. Since the current is going to go in the same direction, the dl vector, or the direction of since the current is guided by the wire, the direction of the wire is going to be our dl element for our differential, or the direction of our current. I think I'm missing an I actually. So to do so, the directions, the dl element is actually the exact same for both of these, which is very convenient. And also, let's choose a point in space that we want to find the magnetic field at. And let's say here, somewhere, let's pick the the y-axis, since here we can let x be 0 and z be 0 also. So let's call this point r vector. And then let's call this r prime 1. Let's call this point r prime 2. Now, let's start from the top down. So here, each of these will have a magnetic field contribution. So let's call this one script R1, and down here script R2. Now script R1 is the same thing as R vector minus R1 prime. And we just discussed, and we'll say that R vector has 0 for x and 0 for z. So this just has distance of y. So let's say y hat. And R1 vector, let's say it has it is x at the coordinate x prime x hat plus y prime y hat plus z prime z hat. And following this, that must mean R2 vector, this is a negative z, like the opposite version of this reflected across the xy plane would just be the exact same thing because they share the same x prime y prime coordinate, but in a negative z. So this would be x prime x hat plus y prime y hat minus z prime z hat. And here we can also just define R2 script R as R minus R2 prime, R minus R2 prime. Now, if we continue to solve for, let's define how much the differential magnetic field contribution is here from the contributions given by each of these 2 points. So here we know the definition of the differential magnetic field component. So here we'll just define dB, or differential magnetic field, from both these contributions is, let's just pull out the constants, I over 4 pi, since they have the same current. And since they have the same DL, we can leave that the same. So DL cross. And since we also can rewrite this, since, if I'll write it up here maybe, because remember, script R vector is the same thing as script R hat. If we replace R hat with script R, we can rewrite this as this, let's call this script R1 vector, and we can divide this by script R1 cubed. Remember, it was squared initially, and we replaced it with script R vector here. And this would be the contribution from the top point, and then we also need to consider the contribution from the bottom point. So this would be DL vector cross script R2, script R2 cubed. Okay, so now the main thing that we have to do right now is find these cross products. But we can also say, since this is symmetric, because each slice that we're considering has the same xy coordinate and has a difference, they have the same magnitude of the z, because this is positive z distance up, and then this is negative z prime distance down. So that would mean the norm of each of these vectors are the exact same, and since we're considering it on the y-axis, which is in the xy plane, each of these points are going to have the same distance to that point. So we can say from here that script R1 is equal to script R2. And remember, these are just the magnitudes of the vectors. So now that we know this, let's calculate this cross product. Well, first we need to figure out these script R's. So script R1 is R vector, which is y hat, minus R prime 1 minus x prime x hat plus y prime y hat plus z prime z hat. And this will get you negative x hat, x prime, plus y minus y prime y hat minus z prime z hat. Similarly, we can say script R2 is equal to y hat minus x prime x hat plus y prime y hat minus z prime z hat. This will get us negative x hat minus y, y plus y minus y prime y hat plus z prime z hat. Now let's compute these cross products. So let's do DL cross script R1 is equal to x hat, y hat, and z hat. And x hat, we have negative x. here we have y minus y prime. Oops, excuse me, this one. It's y prime and then negative z prime. Oh, excuse me. Let's try this again. DL vector is, let's consider this DL vector real quick. And each of these slices, since each slice is perpendicular with the z-axis, they actually only have, this DL vector only has an x and y component. And let's call it a dx prime and a dy prime. So DL vector cross script r is equal to x hat, y hat, z hat. Since there's no z component, there's 0. I say dx prime, dy prime, and then negative x, y minus y prime, minus z prime. And doing this, we can find it using the determinants, right? So here it's x hat and determinant of this matrix. So there's obviously nothing here, but so that we are left with negative z prime dy prime. For the y, we do minus, and then determinant given by this. There's 0 here, minus z prime dx. Oops, y hat, negative z prime. Oops, negative z prime times dx prime. And then plus z hat, and then this matrix, which is y minus y prime dx prime plus this x dy prime. I think this is y x prime. Oops. Oh, I'm missing this. Okay. There we go. Now that's for script R1, and let's consider script R2. Remember, they're the same DL direction, so we can say dx prime, dy prime again, and 0. And then script R2 is negative x prime, y minus y prime. And this is positive z prime, okay? I think you can kind of see what's going to happen. So if we do this again, the determinant of this is z prime, z prime dy prime, minus y hat of this z prime dx prime plus z hat of y minus y prime dx prime minus plus x prime dy prime. All right. Okay, so if we go back to this equation where we define the differential element, we can say that dB vector, and we also remember we said that the script r had the same magnitude, so I'm going to pull out a script r1 cubed, mu naught I over 4 pi divided by script r1 cubed times dl cross script r1 plus dl cross script r2. Okay, so now we just need to compare these two terms that we have here. And you can see actually that here, since they are symmetric about the z-axis, and that would just mean they have their z components are plus minus of each other, right? So here in this cross product, in these two terms, if we compare them, in the x hat, there's a negative z prime. Here's a positive z prime. So actually these two terms will cancel. And then in the x, there's a minus minus. So this is plus z prime dx prime in the x hat direction. And this is a minus z prime dx prime in the y hat direction. So these terms also cancel. These terms are the exact same when we sum them. So this becomes mu naught I over 4 pi script r1 cubed, and we can say 2 z hat y minus y prime dx prime plus x prime dy prime. So here we can see clearly that given that our infinite solenoid has a constant shape along its length, we can always find, for every point in space, two slices of the solenoid such that the current will cancel out each other in the xy direction and only have a parallel component, or parallel to the z-axis, or the parallel to the length of the solenoid axis. As you can see, only the z direction here. So that's the first part of our problem. And to show that the field, let's consider the let's figure out the magnitude of this field. So here, let's consider a slice of this field in the YZ plane. So what this will look like is roughly like this. And based on, so remember, this is Y and this is Z. So based on what we did earlier, this current is traveling with in a counterclockwise direction, right? So if I do right hand rule from my thumb, on the right side, the current goes into the page, and then on the other side, it comes out of the page. So here, current comes out of the page, and here, current goes into the page. So now we can use Ampere's law. So let's consider two loops here. So first of all, let's do a loop that wraps part of the wire, and then another loop that is completely outside of the coil. Let's define this length here to be A, this length to be B. Excuse me. Sorry. Not this. Let's do this. Let's define this to be A, this to be B. Let's solve for this loop first. So by Ampere's law, we know that the integral of the magnetic field over the dl vector is not I enclosed, correct. So over this, the dl is going to be defined by each side of this Amperian loop that we have created here. And let's say the direction of it's like this. Now, on these sides, on the sides that point radially outward, we know that the magnetic field has no component. So these actually can contribute 0 to this integral. And then that would leave us actually with, since it's dotted both directions, this integral boils down actually to B vector at this farther point, so B, minus B vector at A, this closer side of this Amperian loop. And since inside of this Amperian loop it enclosed no current, this becomes 0, and you can see that BB is equal to BA. And then given the constraint that the magnetic field as R goes to infinity, B has to go to 0, we can see that the magnetic field outside of this coil is not dependent on the radial distance from the center of the coil. And that would mean for all points outside of this coil, there's no magnetic field actually. So knowing this, we can also solve. That means B is 0 outside. Now, I'm running out of space here, but let's figure out the last part of this Amperian loop that encloses some of the coils here. So, since the last part, actually, let me see. Inside this coil, so let's consider this Amperian loop that wraps partially inside of the loop, inside of the solenoid, and outside of it a little too. If we look at this integral for outside of this loop, since this b is 0 outside the loop, this becomes 0. And then these perpendicular components, or these radial components, are also 0, because we know the magnetic field is in the direction of the axis of the solenoid. So only this part of the Amperian loop has a contribution to our magnetic field, or sorry, to this integral. So knowing this, the current, we have 1I for each of these coils enclosed by this Amperian loop. So this integral, it just boils down to the magnetic field times L, because let's say this is length L, right here. And we don't consider any of these three sides because magnetic field is 0. And the total enclosed current would just be each of the number of coils that go through this Amperian loop. So we can say mu naught n, where n is the number of turns, I. And that would mean that, so that means we can rewrite this as B vector for, this is for the infinite solenoid now, is mu naught n I over L in the z hat direction inside the coil, and 0 outside coil. Okay, so now that we've shown that this, for infinite solenoid, that it boils down to this magnetic field down here, the last part of this problem wants us to show that for a toroid, which is essentially a solenoid but wrapped around and connected to itself, if you have a large enough toroid, so if you have a donut large enough, essentially, that each, if you, in the perspective of, say, an ant looking at a massive donut, each of this, it would just look like if you were walking around this large donut, it would just look like a long tube to you. So then you could essentially say that this large donut looks like an infinite solenoid or infinite coil. So up here, I have the toroid field. And actually, since this toroid, this toroid field, this part of this toroid field, right here, n over 2 pi s, is actually, we can define a, what do they call it, a wound, the number of turns per unit length. And they can say this is little n also. So they allow this, so if we allow this toroid to become so large, then it boils down to essentially the same as the infinite coil that we have here. Because if we say the infinite coil right here, this length, we can make this Amperian loop as long as we want. And let's say we make this donut really long, such that each side is essentially straight. Then we can say this length L, which would be the entirety. Let's say we make this loop. Let's say this is our toroid, and we draw an Amperian loop like this, a rectangle that encircles the inner side of this coil, like this side. If we define this Amperian loop, this inner side would just be a 2. This inner length would be 2 pi s. So when we let this infinite solenoid, the length of this Amperian loop inside would be 2 pi s. And when we do so, it boils down to just our toroid field. Or sorry, our toroid field just boils down to, if we rewrite this becomes mu naught n I, which is the excuse me. This reduces down, this is essentially the same as our solenoid field. All right, thank you.